Hello. So today we are going to be talking about one of the best topics in all of chemistry, that of significant figures. We actually already started talking about this the other day with the popsicle stick lab. You'll see there was a good reason for that. Significant figures take into account the fact that in science, unlike in math, we use tools to help us gather information, and those tools have varying degrees of what's called uncertainty. So they're calibrated so that you can read particular digits, but then you have to estimate some digits as well. So there are two kinds of numbers, as you can see in scientific work. There are exact numbers, counting type numbers. So you know, if I count the number of students, I know exactly how many students there are in the classroom at any given time. These are also numbers that are defined. In the metric system in particular, we have very clear definitions of numbers. So 1 meter is exactly 100 centimeters every single time. So those numbers, since they're known exactly, we don't have to worry about them. Things like conversions, like from English to metric, those get a little bit more fuzzy, but for our purposes, at least, we can say that those numbers are exact as well. So those aren't the kind of numbers that we're really going to be talking about in regards to significant figures. The numbers we are going to be talking about are these, inexact numbers. So these are numbers that are obtained by measurement, and they have some uncertainty because your measurement value is only as good as the tool you use to make it. And so if you're using, our single unit popsicle stick where there were no markings on it, we're estimating basically the entire measurement. If we use our stick that was divided into 10, right, then we know a tenth with certainty, and we have to estimate the next digit, the 100th. We could, and as scientists, we have gone further and further and made more and more demarcations on our tools, like on meter sticks. They have millimeter values. And so as you add more and more demarcations on your tool, you're taking the uncertainty and kind of diminishing it. So you're getting closer and closer and closer, hopefully, to a more exact value. But there's still going to be some uncertainty in that value because you still, when we measure in science, you still are always going to estimate the last digit. So we'll talk about that more in just a moment. So when we're talking about numbers, scientifically, when we're talking about measured numbers in particular, the significant figures are all the digits that we know for sure from our tool, our measuring tool, plus the one more that we estimate. So if you look at this thermometer here, you can see there are divisions of 1 degree marked on the thermometer, 1 degree, 2 degrees, 3 degrees, etc. And so if you look at the question, it's asking what's the right way of recording the temperature, 27, 27.5, or 27.58. Okay, the way you report a measurement scientifically, okay, and so the way you all will record a measurement is by saying all the digits that you know with certainty from your tool. So if we look at this, we know that it's 20, 1, 2, 3, 4, 5, 6, 7. It's somewhere between 27 and 28. Okay, and so we can estimate that it's about halfway between 27 and 28. So looking at these options, we would choose 27.5, okay? 27.58 is too specific for the tool that we're using, okay? One thing about this, and we saw this a little bit in the Popsicle Lab, is that each of you may have a slightly different value for your final digit. You might have thought when you first looked at it that it was 27.4 or 27.6. Okay, those are okay since that last digit is estimated. Okay, so each person, to a certain extent, is going to estimate a little bit differently. Okay, so if we follow this rule that measured quantities are reported so that only the last digit is uncertain, that means that if we look at the number that is reported by someone's measurement, we know something about how good the tool was. Okay, if the temperature value that was reported was just 27, then we would know that on the thermometer there were just the 20 mark and the 30 mark, and we would know that the 7 was an estimate. So it's important that numbers are reported in this way because scientists world over know that the number tells you about the tool. Okay. So far, I don't think this is too different from what you've learned before. The tricky things happen more so when we take these numbers and then we do calculations with them. So when you do calculations, it's important to know what numbers are significant. So that's all the known digits plus the one estimated digit, okay? Because which numbers are significant comes into play with how you report a calculated answer. So there are some rules for Sig Figs that you just have to learn. And we will use them all year long. So become familiar with these. So the first rule is pretty easy. Non-zero numbers are always significant. So if there is a digit, it is significant. It means it was measured or it was the last estimated digit. It's there for a reason. Easy peasy. The next rule is the rule that I call the sandwich rule, because the zeros sandwiched between significant figures or digits, they mean the same thing, are always significant. So here you can see 20.6, the zeros in between the 2 and the 6, and so there are 3 significant figures. Same goes if we have 20.06, 2 zeros sandwiched between the 2 and the 6, so there's 4 significant figures. There could be 73 zeros in between the 2 and the 6, and there would be, 75 significant figures. Any zero that's sandwiched is significant. That means it was measured or it was the last estimated digit. Okay. The last rule is the trickiest rule, I think, for most people. And it is the to the right rule. Because in order to be significant, if they're not sandwiched, zeros have to be both to the right of the decimal and to the right of a significant figure. Okay, they have to be both. So notice here, if we look at this number, 0.040, these first 2 leading zeros, they're not sandwiched between anything. They're not, well, this one's not to the right of the decimal, This one is to the right of the decimal, but it's not to the right of anything significant. So they are not counted in our significant figure rule. So this number, 0.40, has only two significant figures. The 4, because it's non-zero, and then the final 0, because it's to the right of the decimal and to the right of the 4. And I'll show you guys sometime, maybe like at the end of Friday, I'll show you a cute little way to help you remember this rule in particular. So, yeah, I will. If we look at 400.0, that, because all of these zeros, well, actually, because this 0 is to the right of the decimal and to the right of the 4, that 0 is significant. Okay, and these other two zeros kind of fall into the sandwich category because they're between the 4 and the 0 that's covered under the to the right rule. Okay. Yeah. The last thing isn't really, well, it's sort of a rule. It's more of a guideline. Zeros at the end of a number before the decimal point, or like if there is no decimal point, like here, that's just 400, no decimal. It's a little bit ambiguous. And so we'll talk about how you deal with these kind of numbers on the last slide. It's number 6, if you're counting. So, calculations are really why we're interested in this whole Sig Fig business. For adding and subtracting, the rules are pretty easy. You actually don't even have to know anything about Sig Figs to be able to add or subtract. So, when you add or subtract, and when you multiply and divide, the goal is to report your answer in such a way that you're keeping true to how good of a tool you use to get your measurement. Okay, so you want to reflect the precision of the original measurements, even though you're doing some mathematical operations to them. So in a calculation, you have to follow these rules. And for addition and subtraction, the answer cannot have more decimal places than the measurement with the fewest decimal places. Okay? Because if you're taking length measurements, let's say with 3 different tools, you need to report your answer to the least specific, the least accurate one. It's kind of like you're only as strong as the weakest link. Your measurement's only as good as the worst tool, basically. So let's look at this calculation. So if we start with the 4, okay, the 4 just has a number in the ones place. It has basically 0 decimal places. Okay, so I'm going to put 0. 1.45 has 2 decimal places. 12.4 has 1 decimal place. So we have to use the value with the least to get our answer. And so our answer can have 0 decimal places. It can only have a digit in the ones place. Okay, now this is the part that people have trouble with. Because if we get this number, if you just add it up in your calculator, if you were in math class, you would get 17.85, and that would be good. And you guys want that to be good, but it's not good because our answer can only have a digit in the ones place. It can't have any more digits than that, so you have to round it off to 18. Now you guys feel like that's inaccurate, and you're right, that feeling is correct. But the reason it feels like that is because the tool we used over here to get this 4 was not a very good tool. And so our number, our answer has to represent that. So go with the feeling, but trust me when I tell you, you have to round because you have to report your answer to be as good as the worst tool, the worst number of decimals. So, of course, there's a different rule when it comes to multiplication and division because there's always a different rule when it comes to multiplication and division. So this is the time when it's really important that you know how many significant figures are in your measurement. Remember, those are all the digits that you know with certainty and that final estimated digit. And then if it's not something you yourself are measuring, if you're getting the measurements from like the textbook or something, then you would use those Sig Fig rules, all non-zero numbers, sandwich zeros, and zeros that are both to the right of the decimal and to the right of a significant figure. Okay, so in order that your answer to a multiplication and division sort of calculation reports the correct number of sig figs to reflect what tool you used, you need to have an answer that has no more than the measurement with the fewest number of significant figures. Okay, so if we look at this calculation, okay, 6.221 has 4 sig figs. 5.2 has 2 sig figs. Those are both easy because they're all non-zero numbers. So if you put that in your calculator, if you were in math class, you would get this number, 32.3492. So that would imply that you were using a tool with a very, very, very small calibration. You had very small divisions, so you could measure very, very specifically. Since you weren't using that kind of a tool, you were using a 5.2 kind of a measurement, you need to round your answer off so that it only has 2 sig figs. So your answer can only be 32. Okay? Again, this is going to seem kind of weird. It seems like you're rounding a lot, but you're doing it to make sure you're reflecting the tools that you use to get the data. We spoke the other day about scientific notation, and this is why. Joe Newman, this is why. So zeros, because of the way the sig fig rules work, zeros can be ambiguous. Sometimes it's hard to tell whether or not they are actually significant. You can apply the rules, but it still can be difficult sometimes to tell. And so you'll see often in, like maybe in your chemistry book or in other scientific writing, often they will use scientific notation because all of the digits that are written in the coefficient in scientific notation, that number, if the digit is written there, then it is significant. So this, if it's exactly 5,000 milliliters, you would write 5.000. And now all these zeros are to the right of the 5 and to the right of the decimal. So they're all significant. So especially if you have a number with zeros in it, the best way to show that those zeros are significant is to write your number in scientific notation. And that takes away this ambiguity that might otherwise exist. So those are sig figs. I will show you the rule sometime this week. If you missed the rule, come and ask me because it's kind of cool. And then make sure you're using these significant figure ideas in the calculations that you do basically for the rest of the year. So enjoy.